So today I'm releasing my first game for the Commodore VIC-20. This is my take on the puzzle game Sudoku. It's written in BASIC and it's designed to run on the unexpanded VIC-20, which means that all the code and data are crammed into 3.5K of memory. The game has some sound effects and all of the source code is available for you on GitHub. So check the link in the video below. You can download it, mess around with it, do whatever you want with it. It's completely free and open source. So for the 9 people out there that do not know what Sudoku is, well, it's a logic-based number puzzle. So the game is played on a 9x9 grid that is split up into 9 3x3 boxes. And throughout the game, you place numbers onto the board trying to fill all the squares. Each row must have the numbers 1 through 9 in it with no duplicates when all is done. Each column will have 1 through 9 with no duplicates when all is done. And each 3x3 block will have the numbers 1 through 9 in it with no duplicates. So the puzzle starts with some numbers already filled in, and the difficulty varies based on how many numbers are pre-filled and where they're positioned in the puzzle. The game includes 11 unique puzzles. There's a few easy, a few medium, a couple hard, and one ridiculously hard one. So to play the game, you can just use your cursor keys to move to the spot that you want. And then when you think you know a number, you press the number on the keyboard to place it into the square. And if you guess correctly, you get a little sound effects and it puts the 2 there. And as you can see, the 2 does not appear in that grid of 9, in the column or the row. But however, you need to be really careful because that is also true for the number 6 here. So in this case, I can press R to pull that 2 off the board and bring my score back down. So no harm, no foul. Now, if I do pick a bad value, like for example, 4 is in this row, as you can see, I get a buzzer sound and I will lose 50 points. So the game will penalize you 50 points for putting bad numbers into squares. And that's really it. Once you fill all the numbers in, the game will end and you'll have your final score. And if you can't win, you can press Q to give up and maybe try a different board. So we're going to press Q here to exit out. So we're going to hit yes. And let's see how much free RAM we have at the moment. Wow, just 44 bytes of free RAM. Yeah, this game runs in 3.5K, but just barely. And when we run it, you get to choose the puzzle. No, I'll choose the 5. It takes a couple seconds to get ready, paints the board, and then off we go. So let me take you on a quick tour and show you what tools I used to write this game. I actually used the CBM prg studio to write it. And of course, the wonderful VIC-20 emulator. So let me grab a copy off of GitHub, bring up CBM Program Studio, and give you a quick tour. So at this point, I've downloaded the project from GitHub, and I've opened it in CBM prg Studio on my machine. And as you can see on the right side, I have my VIC emulator for the VIC-20 running. I'm going to start by opening up an empty BASIC file just to give you a short tour of how to program BASIC using CBM Program Studio. It's actually really quite cool. So on the right side, of course, is a VIC-20 running that has nothing happening yet. And on this side is where we can type our basic program. So we'll just do our classic hello world kind of a thing. So we'll just do print hello world. You want to drop into this gear for a moment and you want to check 2 things real quick. First thing in project is you have to have a value here. If you don't have a value here, you'll get an error just from closing the dialog. In emulator control, you want to put the fully qualified path name of the VIC-20 emulator, and that's where mine is on my machine. So we're just going to hit OK. So with this program typed in, 10 print hello world, I just press F5, and it's going to build it at the bottom of the screen, and it's going to restart the emulator and run the program. And there it is. So the first thing you'll notice in the editor is the number 22 in the gutter next to my first line of code, which is 10 print hello world. Actually, I'm going to make this a little bit bigger. I'm going to hold down a control key and just use my mouse wheel to kind of blow that text up. That 22 in the gutter represents how many bytes of memory that line of BASIC takes. And we can prove that on the right side by typing in the total memory that BASIC has when you start, which is 3583, minus free 0. And that's a function in BASIC that tells you how much memory is free. And we can then see how many bytes we've used, and it matches. So this is really, really useful. Because we're writing code in such a memory-constrained computer, every byte counts, and it's nice to have a tool that tells us how much bytes each line is. So on the VIC-20, there's also special characters that our IBM PC compatible keyboards don't have. So if I were to new this program, for example, and I was to type 10 print clear hello world and run it, it would clear the screen and show hello world. So in CBM Program Studio, we can use an emulated keyboard just to get that keystroke in. So what you do is you move the cursor right after the quote, you press F4, and this brings up a little virtual Commodore keyboard. And on a Commodore keyboard, you're going to press Shift Clear Home, and you're going to see that it put this word clear in curly braces here. We're just going to press Update, then we're going to close this window, and you'll see that it typed in curly brace clear curly brace. Now, if I were to run this program with F5, it'll translate that into Petsky, and I get a clear screen in Hello World. You'll also notice that it's smart enough to know that this, in a Commodore, is one character, so it counts it as one character here. So, again, super duper useful. And if I list it on the VIC-20 side, you can see that the clear character is here. Another important feature of using CBM Program Studio that makes life easier is constants. So let's start by using something that you may or may not be familiar with VIC-20, and that's memory location 36879, and we could put a value of 10 there. Okay, 36879 on a VIC-20 is an area of memory that controls the border and the screen color. Actually, and another flag called the inverse flag, but I'll just ignore that for now. 10 is a color that'll give us kind of like a red border and a black screen. So if I were to run this with F5, our program looks like this now. Now, in terms of constants, I know this memory just because I've played around with the VIC-20 for quite a bit. But reading the source code, it just looks like a magic number. So one of the cool things you can do is you can create constants. And you do that with an exclamation point and a dash. And then we type in CONST in all capital letters. We'll give it a name. We'll just call this, I don't know, colors. And then we'll give it a numeric value, 36879. And then in our code here, we can just type in the word colors. And then when we run our program on the VIC-20, it'll still work. But when we list it, you'll notice that it's substituted the word colors for 36879. So CBM Program Studio gives you some tools to make your code more readable, but it'll still compile to Commodore code. This gets really useful when you start using all sorts of different interesting memory locations throughout the memory map of the VIC-20 in your code. It'll make your code more readable. You'll also notice that this particular line of code did not come across because it's a comment. Constants are a special comment, but we can do things like this is my program. And this will just be completely ignored when I bring it over to the VIC-20 with the F5 key. Pretty neat. So I'm going to add in yellow here. So I'm going to bring my virtual keyboard. We're going to press the control key. We're going to choose yellow. We're going to update our code with it. We'll close this. This way our screen's a little bit more easier to read. And we'll talk about crunching your program. On the Commodore, when we run this again, if we list our program here, crunching is getting rid of any extra space to make the program smaller. So again, if I show you the memory used by a program, there's 39 bytes used. If I were to take these extra spaces out that aren't needed, and a program will still run the same, I freed up a couple bytes of memory there. We can do that on this code over here, but it makes our code a little bit more harder to read. So a really neat feature in CBM Program Studio is the ability to have it automatically crunch our programs for us. So if we go into this little gear into the options, and we go into the basic code generation section, there's a little checkbox here that says include spaces. If we uncheck that, and we'll hit OK now, we're going to run our program again with F5. It'll crunch our program on the VIC-20, saving us some memory, but our code is still quite readable in our Windows project here on the left side. Now that we've covered the basics of writing BASIC with CBM Prog Studio, let's take a look at the Sudoku code and see how it works. So now we're looking at the basic source code for my Sudoku program. And you can see here I like to do a lot of comments. So the first block just kind of describes the program, the YouTube channel, and some version history. It shows here that I wrote it in CBM prg Studio. I think technically this is .prg Studio, but I'll forgive myself this time. And there's a little hint here to go into an option and make sure you uncheck include spaces. And I'll show you in a moment the impact of having that and not having that, especially with a large program like this. So the next section here is I have comments where I describe each variable I'm using in the program and what it does. This will be really helpful for myself when I come back to this program, maybe a year from now, to take a look at it. These two-letter variable names will probably not make much sense when looking at the code, so it's nice to have a little map of that at the top. And then I have a whole section of comments where I describe the memory locations and kind of what they do, so it makes my code a bit easier to read. So before we dive into the code, let's take a few moments and talk about our choice of variables and variable types. So the Sudoku game board, as you know, is a 9x9 grid, and it might be tempted to declare your game board like this. And if you look at how much RAM that uses, that's 511 bytes. So there's a couple quick things here about Commodore BASIC that are interesting. When you dimension an array and you put in these two numbers, it's not the size of the array, it's the highest index of each dimension. So here it's actually a 10 by 10 array because it's 0 to 9 by 0 to 9. So just by making the array the right size, I can go from 511 bytes of used memory back down to 416. So pretty significant impact. Now, when you declare variables in Commodore BASIC, and you don't put a type next to it, by default they are floating points, where that means that each cell in my array takes up 5 bytes of memory and is a floating point number. Well, we don't need floating point numbers. We just need to store a number between 0 and 9, 0 being an empty space and 1 through 9 being the number put into that square. So a better choice for us is to use integers, and that's what GB% is. And here you'll see it goes down to 173 bytes. So picking the right type of variable to store your data, especially in VIC-20 BASIC, is really important because we could have wasted a lot of memory for no reason. A minor interesting thing about Commodore BASIC is this too, right? The type of variable are completely distinct from just the letter A. So for example, if I run this command and I print A%, and $1, you will see that they are 3 distinct variables. So you can use the same name with different types and they are different variables. So technically you can have 6 different variables with the letter A, whether it's A%, or $1, or you can declare arrays the same way, and these are all different arrays, and you'll still have these variables here as well as 3 more variables with the letter A, but they are arrays. Sometimes it makes sense to do that, sometimes it doesn't. I'm actually using that in my program a bit here. So if you go back to my code, you'll see that I have GB%, right? That's the game board that we picked when we start the game, as opposed to the array that is the game board. So let's take a quick short tour through the code here. I have a couple of variables that I declare right away. One is this blank space 1 to 9. I use this to quickly turn a key into a string to print onto the screen without doing too much string manipulation. A lot of string manipulation in a basic program can chew up memory. So I'm trying to minimize any kind of string concatenation that I'm doing in the code. These are just various variables I'm using. This sets our color to that black and red border. And then here I'm turning the sound volume way up. And the very first thing happens when you run a program is it asks you for what puzzle you want to do. If it's invalid, it ends. Otherwise, it goes and it loads it in, and we'll show you that in a moment. Otherwise, it goes subs 800, which is the entire game. And then when a game loop is completely done, it exits out. So this is a really short entry point to the program. So let's first go into here and see what happens if we leave the include for spaces options checked. So if I hit F5 to run this, the program will come up. I'll choose a puzzle, I'll hit F5, and I run out of memory, right? Because this program just barely fits into the amount of memory. So it's very important that if you're going to be playing around with the source code for this game that you turn off include spaces. This will crunch the program and let the game run without a problem. So we'll choose board 1. That's the one moment here. It goes up to 800. That's the whole game, and it runs. So there's a couple routines that I have in here, and I could probably use constants to name these routines. That would probably make the code even more readable, but 8,000 and then 7,000. So what is 8,000? I'm just going to jump down here a little bit. 8,000 is a routine that will read in the game board from data statements and get it into the array. All right, and I'll cover that in a moment because that's actually kind of interesting. And then when it's done doing that, it goes to 7,000, and 7,000 is where we paint the board. That's that part where you saw where it painted the whole board. Then it comes back, and now this is just kind of the loop here. Going to 1,000, which is right here. This basically waits for the key and handles moving the cursor and all that kind of logic. LF% is how many pieces are left in a puzzle. If there's none left, it goes to 4,000, which shows you that you've beaten the game, and then it returns back up here and then ends. If you were to quit the game by pressing Q, it sets a variable called QT for quit. And if that variable is not set, it just goes into an endless loop. And then when you do quit, it bounces out and also ends the game. So these are kind of your two main loops. This starts the game, and this is the really tight loop that kind of controls the flow of the game. This 1,000 here is where we wait for key press. Now we do a couple interesting things here. You'll notice that the cursor is blinking, so these two variables CX and CY are where we are in relation to the game board. 0 through 8 in both X and Y directions. PX and PY I call poke X, poke Y. So basically I'm going to copy those variables in 0 and 0. I'm going to set the color to yellow, right? And then what I'll do is I'll kind of offset it so where we're poking onto the screen moves it across. So for example, 0, 1, from greater than 2, it adds another one to jump over that line. And that's kind of what this little block of code does. Now this is kind of interesting here. When you do move the cursor, when we do figure out where the X and Y is, you can call the kernel from BASIC. So we're going to set the CPU flags to 0. We're going to set up the X register and a Y register. So this is kind of like almost like assembly, but not really. And then we call this routine called kernel plot, and that just moves the cursor to, the new calculated position on the screen. So once the cursor is in position, I will set the blink of the cursor so it starts blinking while we're just waiting for a key. We'll clear out the character buffer, and then we'll use the wait command in BASIC to wait till a key appears in a buffer. Once a key appears in a buffer, I turn the blink off, and then I have to make sure I turn the reverse video off because you don't know what state the cursor is going to be in when you come out of that routine. And then I clear out the buffer again to make sure nothing can override it. And then $, becomes the first character in keyboard buffer. So this is just a really long way of saying wait for key press, put it in $. This part's really kind of cool. With the VIC-20, depending on how much RAM you've got plugged into the cartridge, 3K, 8K, or no expansion, the physical memory address of the screen and a color RAM kind of float around to different places. By reading the content of 209 and 210, we get the memory address of the line that the physical cursor is on, and then adding in 211, we can add the column across. What we're doing here is we're reading from it and we're turning off the reverse video. That's what the AND 127 does. And then we're also adjusting the color ramp to make sure that it turns white instead of yellow. Also, if you run this on a Commodore 64, the same memory locations do the same things, this code will actually work exactly the same, and that has memory in a completely different location. So this kind of makes our code here almost cross-platform. And the rest here is just kind of, you press a key, move things around, quit, pulling back a value, and then returning. The rest of this code is pretty straightforward game logic. Place a piece, we do some logic here to figure out, does a number exist on a row, right? So if I press 2, there's 2 in a row. If it is, we play a buzzer sound, we go back, and it kind of just goes through that logic. This is where you win. There's a logic for moving a piece off the game board, just updating the score so you don't have to repaint the whole screen. This is the code that makes the different sound effects. This is when I was writing the code looking for memory leaks. I would have, every time the board would repaint, I would print how much RAM is free. So I left that code commented out in case I ever needed it again. what's really interesting is how I was able to pack 11 boards into 3.5K, right? So this is what it looks like. So I'll just kind of explain to you what it's doing. I mean, you can read it in the comments here, but I'll just kind of explain to you. So I have one of these books that I bought from Walmart, which has a bunch of Sudoku puzzles in it. And if you were to take a board, it might look like something like this in data statement. So you have all this room. So one thing we can do is, we know that each cell takes a value between 0 and 9. We can fit 2 variables into one number knowing that. We can split that into 2 sides, right? So if this is 4 bits, each one of these can handle 16 values. Well, we only need 9 on each side. So I wrote a piece of code that takes each pair of numbers and compresses it into one value. So effectively what happens is you end up with half as much data than you would need before, because I'm packing them into 1 byte each. These are obviously not the right answers, just trying to give you a visual of what it does. Then on top of that, in BASIC, you don't actually have to put a 0. You can just leave them as blank commas, and it reads as a 0. So all of a sudden, that big board we had takes a whole lot less space in RAM. So now converting that is kind of a pain. So I have a little program that's in this Git package called packboard. And what you do is you type in a board from a magazine like this, right? The last one I typed in is diabolical. And if I just hit F5 to run this program, over here it just prints out the data packed into 2 lines. And then I would just type these into the puzzles down here. And again, you don't need the zeros. And you can see diabolicals here, 128, 009, etc. Oh, look, I forgot to take out the zeros. So we could definitely save more RAM here. So what happens when you rush at the very end of your project, right? So that's kind of the source code of the program. And of course, as you can see here, there's a tool to make your own boards called Packboard. And as I talked to you before, you can just type this in from a magazine, run this code, and you'll get this data statement you throw in the bottom, and your board is all set. In terms of the difficulty, I just knew from when I was typing them in, 1 through 4 was green, 5 through 8 is yellow. But you could, of course, bring in all red boards that are really hard or something like that. So that's pretty much it. That's the Sudoku program. If you were to run this on a Commodore 64, the only thing you would have to change would be the screen color here, and then you'd have to rewrite the sound routines using the SID chip. But the rest of the program would run as is. I would presume it would work the same on the Commodore 16, but I haven't tried that. I don't know if these memory locations are the same on the Commodore 16. So I hope you enjoyed watching this video. If you are going to use CBM prg Studio, please donate some money to the gentleman that wrote it. He did a fantastic job. I mean, it is just such a crazy cool tool, and I'm just using it for basic at the moment. There's just, oh my god, there's so much more to it. I can't wait to start playing around with the screen editor and the spread editor and all the other cool tools that are baked into it. So, but yeah, thanks again for checking out this video, and I'll catch you all later. Take care.